All right, here we go. We got a big box and we have a small box, and they are in equilibrium. They are in static friction, meaning just if one more box, if one more feather, if one more piece of weight was added to little box M, then boom, it would start to slide. The question is, how big can mass M, lowercase m, be before everything starts sliding? So how big can the little mass be before everything starts to slide? So in order to do this, we know that this box system needs to be in equilibrium. We know that everything needs to cancel out. The net force in every dimension must be equal to 0. What we need to solve for is what mass m, lowercase m, will make that happen. So the first thing is we need to see what we need to solve for, which is m. The next thing is we need to know what we know. We know big M. We know G is implied. We know angle theta, and we know the coefficient of static friction. All right, next is we need a diagram. Now this diagram is going to be of the smaller box, mass M. So here is mass M. Now, we're going to tip our axis, so that's why I have drawn it at an angle. So the forces acting on box M are gravity, which is going straight down. Also, the normal force, which is going straight up. Okay, but now here's the challenging part. The small box, what's preventing it from falling is first its own friction. Right? It has friction, static friction, that is resisting itself falling. But also, the larger box, if you follow the rope, also has its own friction. And it's the friction of the larger box, mass M, that is the force in the rope. Right? It is the force that's helping the smaller box from falling. It's preventing it from falling. So that's why we draw two forces. They're both static friction, but one of them is from box capital M, and one of them is from box lowercase m. So there's our free body diagram. So from here we tip our axis. We have our x-axis, we have our y-axis. The angle theta belongs between the y-axis and the force of gravity. From here, we look back and we say, all right, we need to know what mass m is in order to keep this from moving. Right, in order to keep it in equilibrium, so what we need to do is set up a net force equation. Let's first start with the y direction. First thing we do is say the net force in the y direction is going to equal mass times the acceleration in the y direction. Well, we know that in the y direction there are two forces. We have the normal force, which is acting completely vertically, and it's unknown right now. Right, the normal force is acting completely vertically. So we will multiply it by the sine of 90 degrees. And then we're going to add it to the force of gravity in the y direction, which is acting at this angle that is sine of 270 plus theta. And all of that's going to equal the mass times the acceleration vertically. But if you look at the block, of course, it's not going to accelerate vertically. It's not going to accelerate up or down in the y direction, the new y direction, the y direction that has been tipped. So from here, we can then simplify. We can go down a step and say that the normal force times the sine of 90. What's the sine of 90? It's equal to 1. So we have the normal force plus the force of gravity times the sine of theta. So what we can do is move the force of gravity to the other side. So we have negative force of gravity times the sine of 270 plus theta. All right, from here, we can open it up one step further, and we can say that the normal force is equal to negative, the force of gravity of the smaller box is going to be little m times g times the sine of 270 degrees plus theta. Now it's important to note, if you look over at the free body diagram, that the force of gravity is coming from the smaller box, obviously. So that's why the force of gravity, we use lowercase m. So there we have it. We've solved for the normal force. But why? Why do we care about the normal force? Well, we know the force of friction in the x direction on the smaller box is going to be dependent upon the normal force. So we can move down. Now that we have the normal force, what we can do is we can now solve for the forces in the x direction. We can do a net force equation in the x direction. So net force in the x direction equals m times a in the x direction. So let's look at all the forces in the x direction. We have the force of gravity of the smaller box times the cosine of 270 plus theta. Plus, we have the forces that are fighting it, the two frictional forces that are teaming up together. The force of static friction of the smaller box times the cosine of 180 degrees, which is -1, plus the force of friction of the bigger box times the cosine of 180 degrees, which is -1. And all of that equals 0. It all equals 0 because, well, we want it to equal 0, right? We don't want a net force. If there's a net force, then this box moves and it slides and it falls down the cliff. And that's bad. All right, but again, we're looking for the mass in this problem. But I don't see the mass. So we need to keep unpacking this further and further until the mass surfaces from the deep, like Moby Dick. So we need to open up each box. Let's do the force of gravity from the smaller box. That's simply going to equal, aha, it has surfaced. Smaller mass times gravity times the cosine of 270 degrees plus theta. Plus, now we need to open up the force of static friction from the smaller box. Now here's where it gets interesting. Okay, the force of static friction from the smaller box can be simplified though, because the cosine of 180 is -1. So we can simply make this negative force of static friction from the smaller box. Same thing over here, minus the force of static friction from the bigger box. And that equals 0. So now that's a much easier problem. We can open it up one step further. And again, we still have the mass that we're looking for times g, the acceleration of gravity, times the cosine of 270 plus theta. Now minus the force of static friction from the smaller box is going to equal simply the coefficient of static friction times the normal force, aha, the normal force of the smaller box, which is what we solved for up here. Right? This is the smaller box. So, continuing on, minus the coefficient of static friction times the normal force of the bigger box, which is easier to find because it's on a flat surface, and that is equal to 0. So now from here, oh no, now we have two unknowns. But have no fear. We already solved for the normal force. So we take it and we sneak it in right here. So when we do that, what we get is this. We get m times g times cosine of 270 degrees plus theta minus the coefficient of static friction times the normal force of the smaller mass, which we solved for to be negative, another mass, another unknown, m times g times the sine of 270 plus theta. And we need another, another parenthesis. What's within that parenthesis is all the normal force. And then we need to subtract mu times the normal force of the big mass. The normal force of the big mass is easy. It's just its weight, m times g. And all of this equals 0. So now, finally, in the last step, the two masses have arrived. There they are. We need to simply now solve for them, doing some algebra. So, algebraically, we see that there is an m and a g in this term and this term, but not in the far right term. So we take the term on the far right and kick it out, send them to the right side. On the left, we pull out an m and a g. We also see that the negatives will cancel out. So what we do is we pull out our m and we pull out our g. And what's left in these big parentheses will be a cosine of 270 plus theta. Now, you think we should write a minus there, but there's another minus in that equation, so it becomes a plus coefficient of static friction times the sine of 270 plus theta. And then we got to finish it out with another big parenthesis. And that's all going to equal the coefficient times big M times G. Now we can divide by all of this except for M, except the G's cancel, which is cool. So we're left with M is equal to the coefficient of static friction times the big mass divided by cosine of 270 plus theta plus the coefficient of static friction times the sine of 270 plus theta. Now, online you may find a solution that has a negative in there. Well, that's because they didn't use the angle 270 plus theta. They used just theta. But either way, you'll get the correct answer right there. So the mass, the biggest mass that will cause this system to stay in equilibrium is equal to the coefficient of friction times the bigger mass divided by the cosine of 270 plus theta plus the coefficient times sine of 270 plus theta. And that will prevent the mass from falling.